All right, everybody. Thanks for joining me during this latest live weather and climate office hour. Apologies for the slight delay here. This is one of the hazards of using the home office setup for these sorts of things is that I was at the front door for a refrigerated medication delivery. To which point, because many folks have reached out, I did have a pretty major flare of my auto-inflammatory disorder a couple of weeks ago. Came on pretty suddenly, and it was pretty serious. So that is the part of the reason for my hiatus from these live streams. You may or may not have noticed it wasn't that long, but it was one of two reasons, that plus some necessary travel in there. So glad to be back. Hopefully going to be managing that a little better after going to war with insurance companies. It's a long story that I won't delve into too much today. But in any case, thanks for the well wishes, thanks for the support, and I'm out of that particular flare right now. As you can tell, if I look a little pale, that is not because of how I'm feeling necessarily, it's because I can't quite get the lighting to have the right amber tone at the moment. So in any case, thanks for bearing with me both over the last couple of weeks and for the slight delay in this session today. So I do want to talk about a number of things related to this summer in California, and in fact you may be able to hear the neighbor's power tool going, which means I'm going to quickly off camera close the open window for better sound insulation there. So it has been in most of coastal northern and central California at least a notably cool start to summer. So talking about places like San Francisco, the San Francisco Bay Area more broadly, so not just the immediate coast, but also the East Bay, the North Bay, the South Bay for the most part, Monterey Bay Area, the North Coast, and then also the region in the Central Valley that is, I guess we could call it, exposed to the Bay Air. So anything within about 20 miles of the Delta breeze through the Carquinez Strait. So talking about Yolo County and even Sacramento at times, has sort of been had a climate this summer that's a little closer to the coast in the relative anomalousness of temperatures, meaning that it's been relatively cool. Certainly relative to recent summers, which were very hot, but even in the context of the last several decades, at least when you were talking about a place like San Francisco or somewhere else along the immediate coast. But inland, it has been, as I've discussed previously, and this has continued, a remarkably different story as you go up either in elevation or east or north directionally. It's been an exceptionally hot start to summer, not just hotter than the coast, which of course is always true this time of year, but in particular more anomalously hot, meaning that it has actually been very hot even by local standards across some of California's most interior inland valleys, and also, and pretty importantly, in the mountains. So talking about the Sierra Nevada, the higher slopes of even the coast ranges above that cool marine layer, and the Shasta Mountains, for example. Coastal Southern California started out the season along with the coastal Northern California zone much cooler than recent years, although in recent days that coolness has gone away, and so now this coastal coolness is more consistently aligned with the upwelling zone in the Pacific Ocean west of the San Francisco Bay Area that generally affects everywhere from about the Oregon border or so south to the Central Coast, just north of Santa Barbara, right around Point Conception. That's kind of the segment of California coast that's most greatly influenced by that cold ocean water upwelling vertically upward from beneath. And I'll talk more about why that has been happening. And this week, in particular, is actually cooler than average, not just along the coast, but generally throughout California. In fact, some places may even see some of their daily record cool highs. Not record cold, overnight temperatures or anything, but days that fail to reach a particular temperature threshold that we haven't seen on this particular calendar date in July. What is remarkable is how that has become newsworthy. If there's a single day where the afternoon temperature fails to reach the previous recorded level, it's essentially newsworthy now, whereas the other dozens of days per year where the reverse is true, where there's a record high temperature, often don't even make the news anymore because they are literally so common that you couldn't possibly make a news story out of each one. But the anomalous, or even in a few cases, record-breaking coolness statistics, and you can usually come up with one that works if you dig hard enough, those make the news because they are actually more newsworthy these days. They don't occur very often anymore, and so it is notable when they do. And so a lot of folks who live in the Bay Area, for example, who moved there in the last couple of decades, have never experienced a start to summer like this. In fact, if you're under the age of about 30 in San Francisco, you probably haven't seen a June, or at least a start to July, as cool as this one. I'm less in favor of using the really short duration statistics because at some point you start to telescope into oblivion in terms of the physical meaning. But it has been notable, certainly, in the context of recent years, and I want to dig into that more in this session and also give a better sense of maybe the bigger picture, because this is not representative at all of what we're seeing globally at the moment with widespread and record-breaking episodes of heat, oceanic warmth that is, on a global basis, not as record-shattering, at least, as it was in the last couple of years, but in specific ocean basins, including, ironically, most of the North Pacific, the water temperatures are now at record-breaking warm levels, again, as they are in the North Atlantic, as they are in the Mediterranean, as they are in the Baltic Sea, as they are off the coast of Japan and the Western Pacific. So I'm going to show some of that data as well. Just a reminder that this channel is sponsored by Reask, a climate tech company that is rethinking extreme weather risk in a warming world. So I do have some graphics I would like to share, and I'm actually trying to decide spontaneously which one I want to share first, since I actually have quite a few. I did, by the way, write a blog post that was published just about 30 minutes before this session started, so if you want a print version of some of the things I'm going to discuss in more depth in this hour session today, feel free to check that out as well at weatherwest.com. Also, at the very beginning of the chat, I mentioned, and there is a link to this video on YouTube, the latest installment of a documentary series on climate change that I've been involved with, both as someone who is on camera for much of the film and also as a science advisor to the production team, is now out on YouTube. And again, that link I posted it right at the beginning of the live chat today. So feel free to check that out, open a tab in the background, or you don't have to tell me if you leave the session to go watch it now, but do check it out. I think if you show up on these live streams, it's highly likely that I'm doing the manual YouTube algorithm recommendation. It's highly likely that you'll find that worthwhile as well. And please do share, because that's a very low budget production, and it is freely available to everybody on YouTube. So really the main goal is to just have as many people see it as possible. This one, by the way, the second installment, is focused mainly on extreme weather specifically in the context of warming climate, including exactly the kinds of events we've seen all around the country this year and everywhere but California, with record-breaking heat waves, record-breaking precipitation events, extreme and deadly flash floods. All those kinds of things are things we talk about in the film, as well as wildfire. So I'll try and add a link again at the end of the session today, but right now there's a link right up there at the beginning of the live chat. Okay, so what I'm going to do is I'm going to share my screen, and I'm actually adding one more link to share, so I have a lot of graphics to get through today. So let me bring that up here. I'm actually bringing up that additional graphic because I also would like to show the seasonal prediction. Just given how much discussion there's been of how this year has played out versus how seasonal models said it would. I think that's worth discussing. Okay, so I think what I'm going to bring up first is... Oh, I know what I'll do. I think I would actually like to bring up the temperature anomaly map for the last couple of weeks, and then also the evaporative demand anomaly. Okay, so bear with me, share my screen. You'll see the infinite mirror, and then you will see what I would like you to see, which is this. Okay, so I'm going to bring my drawing tool up as well here. So what we've got here is from a courtesy of climatetoolbox.org, another example of strategic state and federal funding at work, is you can see essentially what this a map of the relative rank in this case, or anomalousness, the departure from average in an ordered rank sense. So here the units aren't units of temperature, as you might imagine. What's being shown is the percentile of average temperatures from the last 60 days, so from about May 22nd through July 20th. That's the most recent update of this product. And what this map is showing is, frankly, a truly dramatic, and I really do mean that, a dramatic contrast between region of near or record warmth across most of the Southwest and Great Basin. So anywhere that is in this bright red color, so this whole swath, at least in patches, that is a region that between late May and the present experienced at or near record warmth, which is to say that's a huge portion, if not maybe even a slim majority, of the Great Basin, the Southern Rockies, the Central Rockies, and then even some isolated patches of the Sierra Nevada and the southeastern deserts of California. And anywhere that is in the orange, which is virtually everywhere else in the region I've encircled here, saw a May through July period that is in the top 10% of all starts to summer in terms of temperature over the last 40 or 50 years. And again, the last 40 or 50 years are already warmer than the 40 or 50 years before that. So the contrast that I really want to illustrate, though, is in California. And it essentially is in this part of the state here that I'm sort of highlighting, that carve-out region that I mentioned. The region inside, in this hashed region, has seen a notably hot start to the summer, so from May through July. Notice that this is a majority of California's land area, and it includes some of the hottest parts of the state, down in the Imperial Valley, in the Death Valley region, etc. It also extends, at least locally, to some of these coastal mountain regions up in Upper Lake County, for example, or in the interior of San Luis Obispo County, for example. But that's in great contrast to this other region in California, which I'll now highlight, right along the immediate coast, mainly in northern and central California, but as I mentioned, also extending inland to portions of the southern Sacramento and northern San Joaquin Valley. If we take a look at this map, this is essentially the part of California that has seen the remarkably cool start to summer that I mentioned. And it's a pretty small fraction of the land area of California, but of course home to a significant fraction of California's population. If you include people in the Southern California metros and the San Francisco and Monterey Bay areas and along the I-80 corridor and the state capital region, that's where most people in California live, and those are the places that have been anomalously cool. But even if you go to other parts of the San Joaquin Valley or other parts of the Sacramento Valley, it has been a really warm start to the season. If you go up to South Lake Tahoe region, it's literally one of the warmest starts to the season on record. Similarly in Reno. This is not to say that it's broken all records, because this percentile mapping misses some of what's happened in the last few years since 2020, and there have been record warm years since 2020. So this map can't literally tell us if it's the absolute record or not. We need to look at a different data set. But this does tell us it would have been record-breaking through 2020, So if there's any warmer years, they would have had to have occurred since 2020. But the main thing I really wanted to illustrate is this. If you look at the difference between the San Francisco Bay Area and the Reno Tahoe area, it's literally the difference between a location that has seen one of the coolest, if not the coolest, starts to summer in 30 or 40 years versus a region that's seen among the hottest, if not the hottest, start to summer in over a century. Right along that I-80 corridor. Pretty amazing. Throughout the rest of the West, of course, in the Great Basin, it's just been super, super hot and dry in the Great Basin, in the Four Corners region, and up in the Pacific Northwest. So virtually everywhere else, including, again, the interior of California. That's why there has been a well above average level of wildfire activity in this region, particularly in the Great Basin, but also in the Central and Southern Rockies. We saw the highly destructive wildfire in northern Arizona near the Grand Canyon that destroyed much of the park infrastructure on the north rim of the Grand Canyon. I believe it was last week or the week before. We've seen other fires that were fairly destructive in other parts of the region. No mass residential structure loss events, fortunately, but some very active fires, including one of the strongest fire tornadoes in Utah that we've seen in a while, possibly since the one we saw on the Carr Fire up in Redding, or the fire vortices we saw on the 2020 Southern Sierra fires. I believe it was in 2020. This was an EF2 fire tornado, and the footage is pretty spectacular, if horrifying, in Utah. Fortunately, no one died, which was not true of the Carr Fire tornado back in 2018. In any case, really what I want to illustrate is that your experience in San Francisco literally could not be more different from the experience of people who live in the Sierra Nevada, who live anywhere in the Great Basin, the Southern or Central Rockies, or the Pacific Northwest. It really is not even just a California thing, it's a coastal, central, and northern California thing. Even down in Southern California, it hasn't been super hot along the coast, but it also hasn't been a notably cool summer either. That really is restricted to, in particular, the San Francisco and Monterey Bay areas, but also the North Coast and these other regions I mentioned here. Okay, so beyond that, what we've also seen, and this is what it looks like in the last 15 days, for example. I've had a lot of folks saying, oh man, this pattern has flipped. It's so much cooler everywhere in the West the last 15 days. But again, that's not really true. It's once again concentrated right along the North Coast into the Bay Area. It's a little more widespread in the last 2 weeks, so it has been cool along the coast in Southern California as well these last 2 weeks. But look again, if you look at the interior coastal mountains, the northeastern mountains, the Sierra Nevada, the southeastern California deserts, this whole region is once again well above average. Hasn't been quite as extremely hot across the Great Basin, but here again there are patches again of near record warmth, and the entire region is well above average, either in the top 2/3 or in the top 10 percentile of all historical starts to summer, which again says a lot in a world that's getting warmer. Notably, Western Oregon has actually been at or near record warm during this period, and that does extend into portions of far northern California in the last couple of weeks, which have seen big surges in wildfire activity as well. What this has meant is that we've actually had a pattern that is very conducive for elevated levels of atmospheric thirst. So we talk about potential evapotranspiration. It doesn't necessarily mean that there's evaporation, but it means the atmosphere wants to exert an evaporational force on plants and the environment. What this means is, once again, this is a percentile amount. This means that in some parts of the Great Basin and interior central and eastern California, the last 60 days have featured among, if not the single most evaporatively demanding period on record for late May through mid-July. Again, that is notable. This is actually a superlative on the dry side, and this does coincide with some regions that have seen highly anomalous warmth as well as lower than average precipitation. In this case, the potential evapotranspiration has also been accelerated by the fact it's been fairly windy, something I'll also talk about. So across inland areas, it's been dry, windy, and hot. In near coastal regions, it's still been windy, but it's been much cooler and much moister. So the situation is quite different, and this product reflects that. You in fact see that along the immediate coast of California, over the last 60 days, we are actually experiencing wetter than average conditions. In this case, not because of precipitation since May, but because of lack of evaporation or lack of evaporative demand, because even though it's been windy, it's been cloudy, temperatures have been low, and the humidity has been relatively high under the fog layer. So I think this map is pretty intuitive, and really does describe what people have been experiencing on the ground. It should be, because this is real world data. This is not a model, these are observations. But what I really wanted to point out is this. Everywhere away from the immediate California coast in this entire region, the atmosphere has been extracting well above average amounts of water from this entire region since spring. And the reason why that's important is what we see is that there's been an explosion in wildfire activity across really most of the West. Not so much in southeastern New Mexico, where it's actually been pretty wet, and then again, not along the California coast, where it hasn't been raining, but it's been cool, damp, and cloudy despite the winds. Very, very different story than across most of the interior West. And to that end, I want to show the watch duty map at the moment, and you can see, yes, there's been some fires in California, there's some new ones popping up today, but the only real fires that have been burning for a while and have reached significant size are actually up in that far northern California region that I mentioned, so notably the Green Fire and the Butler Fire, each of which are nearing 20,000 acres, so a combined 40,000 acres. By the standards of the last decade, these are not particularly large fires, although by the standards of most of the 20th century in timber, which is where these fires are mainly burning, those would have been pretty big fires. And again, these are not particularly threatening fires in the sense that they're not moving super quickly, fire weather conditions are not particularly extreme, and they are not directly threatening populated areas. You can see this one has been hemmed in pretty well. I think that's actually an arm of Shasta Reservoir, one of the distal arms. If you look, it's actually connected to the lake, so that's a nice natural, or I guess technically man-made, but sort of natural because it's a body of water, fire break here. And then if you look over in the Shasta Trinity Forest, or actually I think this is up in the Trinity Wilderness, maybe closer to Six Rivers, maybe burning across the boundary there. The Butler Fire is still more active. You can see actually, I think these are probably some burnout operations along a ridgeline or something down here. But this fire remains active, and there are some local evacuations, although again, this is a pretty remote region, not a lot of major population centers here. So, these kinds of fires, when they're burning at a slow to moderate pace across the landscape, in ecosystems that are adapted to fire, can be in many cases a net positive, as they sort of act as unplanned pseudo-controlled fires on the landscape, achieving some of the same benefits that you would get from more intentional prescribed burns. These were, I believe, both naturally ignited. These are both lightning fires from those thunderstorms that I talked about a couple of sessions ago. There were a bunch of other lightning fires that ignited, but all of them remained, I think, under a couple thousand acres, and all of which are now contained or extinguished. These are the two that remain active, and it actually looks like the Green Fire is now considered largely controlled. The Butler Fire remains the one that is particularly active. It has been putting up a fair bit of smoke, but I think the good news is it's going to probably help achieve some of those wildland use or sort of multi benefits from wildfire events that are, again, not planned, but occur in a place where you could have had a prescribed fire to do some good and do some risk reduction. And unless these really take off under some extreme fire weather conditions in the future, which seems unlikely right now, these are probably fires that are going to do more good than harm, even though they were not planned prescribed fires. So in any case, those are the two significant fires in California. You can see there's other initial attack, there's small events, there's a couple, looks like there's a new one in the Sierra Nevada, but again, none of these particularly large, fast-moving, or threatening at the moment. The same cannot necessarily be said for the other fires around the west. These are the fires up by the Dragon Bravo fire. It's not a huge fire, but again, the context is everything, and this did this did cause significant damage, if not near essentially destroying most of the national park infrastructure along the north rim of the Grand Canyon. So the visitor centers and the lodge and all of the campgrounds and things like that in the vicinity. It also caused a chlorine leak because of the local water treatment plant also burned. So there was a period of time, a week or so ago, where there was both a large cluster of structures on fire, a hazardous materials event, and a wildfire ongoing in the Grand Canyon. Tricky for the incident management team, to say the least. Other fires of significance in Utah and in Colorado, western Colorado mainly, and then again up in the Pacific Northwest. There is quite a bit of fire activity in Oregon and Idaho and Washington, and then this map, Washington doesn't extend up into Canada yet, I believe, but there's a lot of activity going on up there as well. If we go to the satellite map, we can see, I'm actually going to zoom in a little bit on this, you can kind of see actually the smoke from that fire up in the Trinity Wilderness that I mentioned. That's kind of, on the quieter days, it's kind of skunking around. On the more unstable and the hotter days, it starts cooking a little hotter, but again, not directly threatening major population centers or infrastructure. There's an interesting cloud feature, actually several, over Northern California right now. This nice linear one is actually, I think this might be some mid-level clouds associated with the very weak cold front that's kind of just, it moved into California yesterday, and it's kind of just been sitting there. Excuse me. Unavoidable, even in the live session. So this is not producing any precipitation right now. It did produce a few light showers and sprinkles across a few parts of Northern California earlier, but right now it's literally just some mid-level clouds. Maybe someone will get a nice sunset out of it. You can see some weaker cumulus clouds bubbling up over the mountains, but no thunderstorms today. There probably will be some isolated thunderstorms later this week in the mountains associated with the unstable air aloft. So if you're on a lake, do be aware that isolated thunderstorms can be just as dangerous as widespread ones if they happen to hit your boat on a lake and you are unprepared. Some interesting little features in the marine layer. This is all marine stratocumulus, so all of these clouds are shallow. They're in the lowest couple thousand feet of the atmosphere. These clouds are probably 15 or 20,000 feet up. You can see that they're moving in a completely different direction than these clouds, and that is, of course, because we have at low levels, these are the surface winds, sort of northwesterly along the coast. The clouds are moving with it, and we have southwesterly flow aloft, and in this case, that's, my handwriting on the screen is not so great, but you get the idea. Low-level winds moving like this, upper-level winds moving like this. They cross each other in the atmosphere. Technically, that would be considered wind shear, but neither this wind nor this wind is particularly strong, and we have no thunderstorms around, so it's not really of any particular significance. But you can see some nice mesoscale swirls and eddies, as they're called, along the coast. You see the little eddy, and this is off of Sonoma Marin Coast. Really, there's topography-induced eddies coming off of all of these topographical features along the coast as you go south. So, that's fairly ordinary for summer. Other little micro-scale eddies in the marine stratocumulus. Always fun to look at the summertime satellite. You can see in the desert southwest, get those things off the screen, you see the mountain and desert thunderstorms popping up of Four Corners region, which is common this time of year. And you can see some isolated wildfire plumes in various places. So, why has the spring and early summer been so chilly? Well, actually, first I want to show, let's show the ocean temperatures first. So here's a current map as of yesterday, which is the most recent data, of current ocean temperature anomalies. The most noticeable thing is how much yellow, red, and orange there is on the map, meaning that most of the global oceans currently are well above average. And there's a couple of regions that really stand out as being above average. One, ironically, is the North Pacific, including the ocean off Japan, which is ridiculously warm. We're talking like 8 to 10 degrees Fahrenheit warmer than average. That is really, really warm water for ocean over such a large region. It'd be one thing for the air to be 10 degrees warmer, but it takes a lot of energy to warm ocean water by 5 or 10 degrees Fahrenheit. Notably, the water temperature off the coast of the eastern seaboard, also very warm. The entire Gulf of Mexico, warmer than average, as is the main development region for Atlantic hurricanes. That's going to come into play later this season, most likely. But also, look at the subarctic ocean off the north of the UK and west of Scandinavia. The Mediterranean and the Black Sea get split, but they're super, super warm as well, as is also, again, split the Baltic Sea. And in general, there's a lot of warm water in the South Pacific and the South Atlantic, most of the Indian Ocean. What stands out as being the outlier here? Well, actually, it is literally this patch of ocean right off the coast of California, which is notable, and I want to zoom in there. Okay, so here's that zoom in. The way the zoom is, it's a little bit wonky, but anyway, here is California, of course, over here. And I want to point out two things. One is the water along the immediate California coast is, in Southern California, not cooler than average at this point. In fact, it's even slightly warmer than average along the immediate coastline. And it's not even that much cooler than average along the immediate north coast. It's right around average. But it remains much cooler than average right now along, again, just west of the Bay Area and off the Central Coast. But look how isolated that is. Look how small this area of really chilly water is relative to usual versus this enormous ocean-sized blob of ridiculously warm water in the west. Well, this little blob of cool water is why coastal California has been so cool, and this super warm blob over here is having a bit of a different effect. In fact, I want to show a little bit more about what's going on later, but I just want to point out this is not because the North Pacific is cold in general. It is literally just a 20 or 30 mile wide strip of ocean just west of the Bay Area that's wreaking all this havoc. But everywhere else, things are pretty much on fire. And that is a striking contrast, by the way. There's patches right off the coast that are on the order of 5 centigrade or close to 9 degrees Fahrenheit cooler than average locally. Well, there's a much larger patch of water offshore that's as much as 10 degrees Fahrenheit above average. So 10 above to nearly 10 below, that's an anomalous gradient, if you will, of 20 degrees Fahrenheit. That is wild. That is an enormous differential, even relative to the background where already, under normal circumstances, the ocean to the west of California would be much much warmer than the ocean right off of California coast. This is telling us that dipole that would normally exist is dramatically stronger than it would normally be. Why is this? Here is something I pulled up this morning. So this is a map of the 500 millibar geopotential height anomaly from beginning of June through 2 days ago. So essentially up to the present, the last almost 2 months. Geopotential heights, again, for those who need a review, are essentially a measure of the aggregate warmth of the lower half of the atmosphere. So in regions that are essentially green and yellow, believe me, I did not pick the color bar. This is the NOAA plotting tool, which I'm grateful exists on the internet, but it is not a great color blindness friendly visualization. I'm well aware. But the point here is that what we've got is an anomalous mid-atmospheric ridge or high pressure system that has been anchored to the northwest of California really since at least since May or June. But the other thing I wanted to point out is that everywhere outlined in green, the geopotential heights at 500 millibar have been above average. That is nearly the entire map except for a portion of northeastern Canada. This is a signature we often see during what is known as the tropical northern hemisphere teleconnection pattern. So essentially a Rossby wave train that emanates up from the tropical Pacific and generates ridginess out over the Pacific and troughiness here. You don't see it as much during the summer a lot of the time, but it does seem like something like that's playing out this year. But the point is, the lower half of the atmosphere has been warmer than average across this entire region. But remember, the immediate California coast has not been warmer than average. So what gives? Well, hopefully this starts to offer some clues. This is now a map of the surface pressure anomaly, so not the middle atmosphere, but the actual amount of pressure at the surface. And remember, the global average surface level pressure is a conserved quantity. You're always there's never an increase or a decrease in the total volume of air on Earth. It's just moving around to different places. It's accumulating temporarily where you have high pressure, and it's dissipating temporarily when you have low pressure. But it's all the same air getting sloshed around and accumulating or dissipating in different places. Geopotential heights can actually rise everywhere. It's not a conserved quantity, and in fact we are seeing large increases in average geopotential heights in a warming climate because, of course, the lower half of the atmosphere is getting warmer nearly everywhere. But in terms of surface pressure, you can't increase pressure everywhere without increasing the amount of mass in the atmosphere. So it's just getting redistributed. And in this case, since June, again, this high pressure, this air has been redistributed to a high pressure center off the coast of the west coast of North America. So this is a pretty robust seasonal scale surface high. Notice how this high pressure is anchored a little bit farther west than the geopotential ridge was, and also it's not as contiguous across the west as the geopotential ridge was. What this means is that we have anticyclonic, or in this case, we have clockwise flow around this high pressure system at the surface. Now, why is this important for the coolness in California? Well, if you think about the air on the eastern flank of this high pressure system, it's essentially doing this. And as the high pressure has wiggled around, some of the time it's doing this, some of the time it's doing this, but there's generally an unusually strong north to south component to the winds. And in fact, I also have a map for that. I have a map for everything today. This is a map showing the relative unusualness of the north to south component of the wind specifically. So this is the meridional, or the north-south component of the wind. Here, purple colors mean that the north to south component of the winds was stronger than usual, and greens and yellows and reds mean that the south to north component was stronger than usual. So this map essentially means that the winds were doing this to an unusual degree. Again, that makes perfect sense if you think about the high pressure system that was there. So the surface winds were unusually strong, blowing from north to south, west of the west coast in this region. You can kind of ignore this little green blob over California. It's a little bit wonky, but the main point is that there's such a large blob of unusually strong north to south winds. That drives, believe it or not, those north to south winds, that drives, and I'm going to bring up this other plot here once again to illustrate. So here's the ocean temperature plot anomaly again. When we have strong northwesterly winds like this, they blow parallel to the California coast. I'm going to draw this inland. Now what happens as you have winds that blow from this direction, again, they're parallel, so I'll emphasize it over here. That actually results in a net force at the surface of the ocean, the net wind stress that is to the right and perpendicular to the wind itself. So essentially this results in a force from that wind that is offshore. What that means is that it tends to pull that surface water to the west or to the southwest, which is directly away from the coast. Now you can imagine, and I'm just going to doodle on the screen off in the corner freehand here, you can imagine if the California coast looks like this. Actually, let me get this to persist. The coast looks approximately like this, and you have water that is getting pulled offshore at the surface. Well, you don't just have the sea level suddenly dropping. That water is going to come and fill the void. So where is it going to come from? It's actually going to rise up from underneath. This is upwelling, and it's rising and replacing that surface water. So in a three-dimensional sense, now if this is the surface of the ocean, I'll draw let me redraw this a little bit. If this is the surface of the ocean, imagine these are the waves. You have water that's getting pulled away from the coast like that. So from east to west, the water from beneath is rising to replace the water that at the surface is being pulled away, because it can't come from the east because that's the Bay Area, and unless there's a body of water in on the land parts of the Bay Area I'm unaware of, it's got to come from somewhere else, and so it comes up from beneath. That is why this region in general off the California coast has such cold water is because that upwelling is persistent, because we often have those northwesterly winds. But this year they are stronger than usual. The upwelling is stronger than usual. The offshore flow of the water itself, that offshore force is stronger than usual, and it has been pretty darn chilly along the coast as a result. Now, a lot of folks are saying, well, this wasn't predicted by the seasonal models, and I think that's probably fair. Although, as I've emphasized earlier, I would like to point out that the seasonal model said that the first half of summer would be highly anomalously hot across the interior of California and the interior west, which it definitely was due to persistent ridging, which we definitely saw, and that would eventually start to spread closer to the coast as we got later into summer, essentially beginning in July. So far, that has not happened yet in July. So it is true that at least for July anyway, the seasonal models are not right about the California coast being warmer than average, although they have been right about essentially everything else everywhere else in the West so far this season. I'm not convinced they won't still be right in a month from now, in August into September, as the natural background state favors a weakening of that upwelling, which may allow the persistence of this ridge to become a more dominant effect. I can't guarantee that because these models are not fine enough in resolution to represent these very fine scale elements of offshore oceanic upwelling. We do not have seasonal climate models that can see the coastline in that way, and so it's maybe not that surprising that they didn't capture it, even though it was important. So what do they say moving forward, perhaps, is the next interesting question. And so if I bring up the most recent update from earlier in this month, this is a forecast from about 10 days ago, and the end of the first week in July, showing, well, what is July? If you look forward to August, this does suggest, again, the potential for strong ridging broadly across the west and above average geopotential heights essentially everywhere. But we go into September, and we see this pattern generally continues with anomalous ridging in the west. That's October. We see some weakness in Alaska, but again, ridging continues across much of the U.S. as we go into fall. What does this mean in terms of predicted surface temperatures? Might be another reasonable question here. And that's what's now being shown here. I just have to bring it up on screen for you. And again, this is from the prediction in July. For August, so for next month, we continue to see that the seasonal models on average suggest that this will continue to spread closer to the coast, so including eventually the offshore waters. It's not a super strong signal, but again, it's hard to get a really warm signal of that magnitude over the coastal region for precisely the reasons we've been discussing. This is for August, suggesting that the warmth will yet spread closer to the coast. This is for September, suggesting that it encompasses the California coast even more going into September and then October. So I still think we're going to see that unusual anomalous warmth closer to the coast, but clearly it's taken a bit longer to get there, and we're not there this month. So July will not have been an unusually warm month along the coast. It will have been an unusually cool year by the standards of the last few decades. Though again, across inland parts of California, the June and July, as had originally been predicted, will end up being well above average temperature-wise. So this is an issue pretty narrowly relegated to the immediate coast or places that sort of have a coastal influence despite being a bit inland, like regions within a certain radius of the Carquinez Strait that experience that delta breeze and therefore that San Francisco Bay marine influence. And then lastly, I want to show the pattern for this week. As I mentioned, it's going to be chilly across most of California. Here is what things look like right now. Again, this is a 500 millibar geopotential height anomaly map from a weather model prediction. This is for right now. If you look out the window, it's pretty cool. It's chilly. There's some clouds. Earlier this morning, there was some marine layer drizzle. Well, you can thank the trough for that. The trough dissipates, but a weak low-pressure system kind of persists over California as general troughiness along the west coast continues for about the next 6 days. But there are once again signs that will begin to fade as we go into early August, and that the western flank of the mean ridge in this vicinity around the four corners, so the ridge over here, that the western flank of that high pressure system will again strengthen to above average levels and perhaps bring another heat wave to the southwest and the interior of California. Will it make it all the way to the coast? I don't know. I think this year it's going to take some stronger offshore flow to really get a true coastal heat wave. But I think that the upwelling is going to be decreasing. Near coastal ocean temperatures will not be as cold as they were, so it's going to get progressively easier for heat waves like this to make more progress towards the coast. And indeed, that's probably what I would expect to see more of going from August into September. So hopefully that provides a little bit of context. There's one other plot I wanted to show here, and it's this one. So I forgot. There's the bonus plot. These are time series plots, again, something I generated this morning using a web tool that I'm grateful exists, because I absolutely would not have had time to code all of these up from scratch today if these were not available. This is NOAA's federally funded Climate at a Glance web tool, and it's great. It really is kind of an amazing on-the-fly visualization tool. But I just wanted to compare this year's as well as the long-term trend in May through June temperatures. On top here, I have San Francisco County, so not just the city of, but the whole county, which, to be fair, is largely the city of San Francisco. There's Shasta County, of course, which is up in Northern California, a more mountainous and interior part of the state. Then I have Los Angeles County here, which, quite contrarily from San Francisco, actually encompasses a region that is much larger than the city of LA and much more geographically diverse, but you get the idea. Mainly coastal Southern California, mainly coastal central to Northern California, and then well into the mountainous interior of Northern California. When we look at this year's value, actually let me make a larger circle here so that's actually visible. When we look at this year's value for San Francisco in the middle there, it's pretty low relative to recent years. It certainly is nothing record-breaking for May or June. It's certainly cooler than the recent average by a bit, and it is one of the cooler years we've seen in the last couple of decades. But if you draw a line, and I'm going to try my best to draw a straight line here, back into the past, what you can actually see is that this temperature would have been significantly warmer than average for most of the 20th century, really up until the 1970s. So believe it or not, the temperatures in May and June this year in San Francisco, they were definitely cool relative to average. And in the last couple weeks, they've maybe even been a little bit cooler. But if you look at May and June in San Francisco, this actually would have been an unusually warm year 50 or 60 years ago in May and June in San Francisco. So I think that is really important perspective here. The other interesting thing is that there hasn't actually been very much warming in San Francisco specifically in May or June since the mid-1980s. I'm not even sure if this trend here would be statistically significant over this 40-year period. It's pretty flat. Now, if you do the long-term trend, that's going to be more substantial and statistically significant, because back in the early 1900s, the temperatures for the May and June, the average temperature would be right around 57 degrees Fahrenheit, and these days it's closer to 60. So that is still several degrees of May and June warming, but at least in the county of San Francisco, almost all of that happened prior to 1985. There has not been a lot of recent warming in this part of the state, which could not be more different from Shasta County. And this is generally representative of much of the interior of California, where May and June in recent years have seen a pretty astonishing rate of warming. In this case, you can actually quantify it. The rate of warming in the last 40 years in San Francisco in May and June has been only about 0.1 Fahrenheit per decade, but in Shasta County, the rate of warming has been nearly a degree per decade. So this is literally 9 times faster warming over the last 40 years in May and June in the interior in Shasta County than in San Francisco. LA is almost exactly in the middle. 4 times the rate of San Francisco, but half the rate of Shasta. And all of this is to say, the world doesn't necessarily revolve around your favorite individual weather station, or even what is arguably a very important county in California is certainly not telling you everything you need to know about what's happening elsewhere in the state. And the most populous counties, if you only focus on these, while it certainly affects more people, that the warming in LA County is slightly less than in a much less populated county of Shasta, this is hugely consequential for folks who do live there and for the ecosystems that are up there. And again, I'm using Shasta County as a proxy, but the story is very similar across almost all interior and mountainous counties of California, as opposed to almost all coastal counties in California. And also, these patterns look very different in the annual average and in autumn. In autumn, all of these places have been warming rapidly. In winter, all of these places have been warming at a similar rate. So it really just is May and June where we have this curious feature, this year maybe extending a bit into July. So it's the late spring and early summer months along the coast where something weird is happening. What is that something weird? Well, it appears to be that this upwelling in early summer has been stronger in recent decades. Interestingly, that's actually consistent with some climate and ocean model projections that the upwelling in the early season, so from late April through the end of June or early July, will probably strengthen as the climate warms, partly due to that strengthening high pressure system that I just mentioned that's really prominent this year, but that upwelling will actually decrease later in the season, meaning that there actually may be a climate change-induced accentuation between early summer coolness and late summer or autumn heat. So we may continue to break all kinds of heat records in the late summer and early autumn months, but really fail to see all that much warming, at least along the immediate coast, due to the increasing influence of that strong upwelling in the late spring and early summer. That's a little bit speculative. There's not a huge amount of evidence for that, but it's certainly consistent with the trend we've seen and circumstantially consistent with some of the oceanic forward projecting models that are coupled with climate models are telling us about the way the future might look. Okay, so I think that's it for the monologue portion today. I do want to go in and answer some questions, and I started a few minutes late, so I'm going to continue past the hour to answer all of the questions that I can that have come in within the last hour. And there's quite a few people online today, which I think is a reflection perhaps of the considerable interest in what the heck is going on in San Francisco and along the coast with the relative coolness as well. So I'm actually going to reshare that link that I mentioned earlier in the video. This is a link to our the second installment of our climate change documentary. It's on YouTube. It's free to watch. It's only about 45 minutes in length. This particular piece is focused on extreme weather, so please do check it out and share it as well. That's taking the place of a commercial break, I guess, before I start answering the comments. Okay, so let's see what we got here. So as always, I'm reading these comments. I don't always read them the moment they come in, but I read them often towards the end of the session and start answering questions live on air for those who have not been part of these sessions before, as I suspect there's a few of you. Yes, there's a comment that there's also been a striking temperature difference up in Oregon. Travel between Portland, which was unbelievably hot, and Tillamook, which was very cool. This has been a pattern we've seen recently, and actually a lot of North America has been very hot. There's been record heat in the Rockies and the Central Plains along the eastern seaboard, where it's also been extremely humid. In fact, there's yet another episode of extreme heat and humidity coming for the eastern half of the U.S. this week. Usually there's a dipole. If it's cool in California, it's usually hellishly hot elsewhere on the continent, and that's certainly what's happening this time around. Ben mentioned some scattered raindrops in Sacramento this morning, probably from that cloud band that I showed, which has been weakening. Comment that New York City is actually pleasant today, below 80 degrees with a pretty mild dew point. That won't hold, unfortunately. I'll actually be in New York later this week, and it's looking like 95 degrees with a heat index of almost 110 because of the humidity. So enjoy it while it lasts, I suppose. Lovely in Salinas, though, Patty says, which is consistent with some of the maps we're seeing today. Mark mentions June gloom, no sky July. I actually haven't heard that latter one. June gloom I've heard before, but no sky July is, I guess, an extension. There's May gray, June gloom, and now I guess at least this year no sky July that follows. That's a good one. Comment from John. It's funny how even the relatively cooler highs still feel hot in Reading. I've noticed the sunlight seems starker and brighter on many days this year. Is it my imagination? Well, it kind of depends. The sun angle does matter, so obviously the time of day, if it's 90 degrees somehow at 9 a.m., which is rare but occasionally happens, it is a more manageable 90 degrees than at, say, noon or 1. And the reason for that is, especially if you're closer to the summer solstice, the sun angle is literally more directly overhead. So the sun's rays have to travel through a thinner column of the Earth's air. They feel stronger because, in fact, per unit area they are. This is one reason why going into the shade helps. It's not because you're actually getting a cooling of the ambient air temperature in many cases so much as you're no longer having the direct solar radiation incident on the surface of your body. So the sun will directly heat your body's surface on an already hot day that can be pretty uncomfortable. You go into the shade, it's still 100 degrees or 90 degrees or whatever it is, but you no longer have that additive effect of the sun's rays actually heating the surface of your body and the micro boundary layer of the air just above the surface of your skin. So I think that might partly just be due to the time of year. Don't know that this year would be special in that regard, because one thing that's not changing is our orbit around the sun, unless I have missed some major astronomical news, which, given the way the last few weeks have gone, I probably could have missed an alien invasion. Yeah, a lot of comments about how absolutely gorgeous it is. And by the way, this weather along the coast in particular, and in the transition region between the coast and inland regions where it's been mild, this is a great season for prescribed burning, in the sense that there's been relatively cool temperatures, no extreme heat waves, relatively good resource availability. It's been breezy, but you actually want some wind during prescribed fires. Not too much, but you want some, because you want to be able to ventilate the air. You don't want the smoke to accumulate and choke people out in the valleys. So you want a little bit of wind and a little bit of an unstable atmosphere to ventilate. So actually, prescribed fire burning conditions, meteorologically speaking, have been really favorable so far, and up to the present in a lot of parts of Northern California in particular. So, and there are some ongoing prescribed burns, although again, as has often been lamented, there just aren't the resources in place right now to do it nearly at the scale that might be most beneficial from an ecosystem restoration and wildfire hazard reduction perspective. So we've had a really good window to do it. We've done some, but probably not as much as many folks would have wished in this window. Yeah, John mentions that there have been some terribly smoky days recently, and that is from those lightning fires. So I did mention that the hazards from those fires was perhaps less than other fires that affect more populated areas. It is unfortunately true that the smoke has been affecting folks in the North Valley in particular, and some of the mountain valleys as well. And that is really hazardous. You can get dangerously high smoke concentrations, even if the fires themselves are not particularly threatening from a destructiveness or ecological perspective. The smoke can still be bad to breathe in, and we've certainly seen that this year. So this has already been a more active fire year, by the way, in California to date in the forests than have been the last couple of years, and we're still away from the peak there. So I still believe that the seasonal prediction of well above average fire activity in California is on track to actually manifest still, and we are on that path at the moment. Yeah, lots of other places around the world with very warm temperatures at the moment. Record heat in Europe, the Mediterranean, in Japan as well. Just a horrific humid heat that's just been unceasing because the ocean is literally almost 10 degrees Fahrenheit above average. There's just no escape on an island nation surrounded by water that was already warm to begin with and is right now 10 full degrees warmer than average in some cases. Yes, I am impressed. Several folks commenting on the number of viewers in this session being higher than average, and I think, again, that's because folks really want to know what's been going on in coastal California. It has been notable. Yeah, that's right. Folks called the 2014 era blob of warm water off the coast of Western North America, perhaps intuitively, the blob. The blob has returned on multiple occasions, and I think it probably is fair to say it's back again. Doesn't mean it's super warm right along the immediate California coast, but as I showed, it is ridiculously warm in that ocean out there relative to usual. It doesn't mean the water is steaming hot tropical ocean bathtub-like warmth, of course, because the baseline is it's a temperate mid-latitude ocean. It's relatively cool to begin with, but in relative terms, it is much warmer than it would usually be. So the blob, I think it's fair to say, is back again. So a lot of other good questions, but I'm trying to focus mainly on the ones that relate to what I was talking about during the session today, so we can focus on some other ones in the next session. A question from Certain Doom on any thoughts on ocean upwelling effects on local fishing and aquaculture. Usually upwelling is good for fisheries and for aquatic animals because it brings nutrient-rich water up from beneath. So often we actually worry more about upwelling being less than average or shutting down, where you get more stagnant water, less nutrient replenishment, and really warm water that animals adapted to pretty cool water in the upwelling zones can't handle. So at least along the near shore for California right now, this should actually be a good thing for coastal ecosystems and for fisheries. Offshore, it's a bit of a different question because the water goes from being really cool on the coast to really much warmer than average offshore. So I'm less certain what it means out there, and it probably is a problem. Ocean temperatures usually vary in such a narrow range that once we start to get up in the 5 to 10 degree Fahrenheit warm anomaly range, that's really, really large, and if it's sustained, that can be really difficult for aquatic species to manage. We've seen that in any number of places in recent years, where marine heat waves, as they've come to be called, have really severe aquatic effects on aquatic ecosystems and the species that live in them. The question from Loretta about whether the odd weather patterns explain the sad performance of the San Francisco Giants this year is, I think, beyond my pay grade, for better or for worse. I suppose you could probably come up with some scientific explanation regarding the density of air, perhaps. There are studies that suggest that there will probably be statistically more home runs, for example, in a warming climate. This has not been a particularly warm summer in San Francisco, so maybe these cool early season games, it's a little harder to hit the ball farther. It's a pretty small effect that probably is usually overwhelmed by the skill or luck of individual players, but in the long run statistical average, there have been studies suggesting that home runs will become more likely due to changes in air density in a warming world. So this year might be the opposite of that at the stadium by the bay, perhaps. So how's that for a mechanistic hypothesis in a scientific paper? There's a question from Kylie about, if I have a chance, could you explain how the wind coming from north to south creates a wind pulling surface water away from the coast. So I deliberately didn't get into the details here because it's a pretty interesting physical science and fluid dynamics topic. But the main process at play, and you can Google this, I'll describe it briefly, but if you want a longer explanation, Google Ekman pumping, E-K-M-A-N, pumping. And the basic idea is that the wind stress from a wind blowing in a particular direction can actually result, an actual wind blowing, just typical, air molecules moving relative to the surface at a particular speed and direction, over a surface of water, will actually result in a net transport force to the right of that flow, at least in this part of the world, at 90 degrees to the right of the wind direction, because of frictional effects within the water itself. So essentially, at the very surface, the wind force is sort of what you'd expect. In the very infinitesimally shallow layer of the water at the surface, the force is essentially the same as the direction of the wind. But then you start to go to deeper levels, and this effect, due to friction, the turning of the wind, or the turning of the force, I should say, becomes more and more pronounced until the net movement of water in the water column and the subsurface actually is at a right angle to the wind. So in this case, the reason why that matters so much is that if we have a wind from the northwest to the southeast, which parallels the coast, turning to the right, 90 degrees to the right of a northwesterly wind, is almost pulling water exactly in the offshore direction. So it's not that the wind generates another wind blowing offshore. It's that northwesterly wind actually moves the water in a counterintuitive direction. It's not exactly parallel with the direction of the wind, but it veers to the right of the direction of the wind. And that transport is known as Ekman transport. So essentially transport to the 90 degrees to the right of the wind. There's also other things going on with respect to gradients in water density, but the main thing that's relevant here is Ekman pumping, and it really explains why California oceans, the California current is cold. It explains why there is such biodiversity in the marine ecosystems here, why there's such robust fisheries, is because there's this persistent region with a lot of cold water upwelling from the deep, nutrient-rich and very cold. This year, it's upwelling even more strongly than usual, and so it's even colder and presumably even more nutrient-rich than usual as well. So, but if you want to know more, Google Ekman pumping. I swear it's not it might get some ads for plumbing companies, but this is a real process, and it's very important in understanding actually upwelling regions in all of the global ocean zones. All right, well, perhaps that's a good note to end on. Again, I shared that link to the documentary. Please, this would be a great time. I'll do it maybe one more time since we're about to close. Feel free to click out now and go give it a watch. But thanks for listening. As always, I encourage you to subscribe to the channel so you get notifications when I'm about to go live. I usually do schedule them at least a day in advance, sometimes more than that. But occasionally during extreme weather or wildfire or other kinds of events like that, I will do live coverage on short notice. And so if you want to hear about those, sometimes you got to be signed up to hear about them before they happen. Although, as always, this session, as all other sessions, has been recorded and will be available for asynchronous listening and viewing shortly after I push the stop button, which I am going to do just about now.